Do you have 9? How many do you have? You have 8, right? It cannot be the same as this digit, and it also cannot be a 0, right? 8 choices. 8 choices. So over here we'll say this one has to be 2, 4, 6, or 8. And this one will say not 0 and not same as 1s. Right? So the total number of 2-digit numbers that have distinct digits and are even is 8 times 4, which is 32. So not the grand total, but maybe the mini grand total. 2-digit numbers with distinct digits that are even is 41. 41. Okay? So far we have 45. We have 4 1-digit numbers and we have 41 2-digit numbers. Okay. And now for the fun part. And this is the one I messed up the other day. We got 1-digit, 2-digit, and now we'll do 3-digit. Where can I do 3-digit? I'll try to do it here. Okay. So when I was playing with this in the math lab, it's amazing what you can accomplish when you can sort of clear your head and just think. Right? Okay, I'm going to start with the ones that end in a 0. End in a 0. You have one choice for what to put here. That has to be a 0. For the middle digit can be anything except it can't be the same as the digit we just put. Well, the digit we just put was a 0, so it can be anything else, right? You have 9 choices for what to put here. So far, so good? And then over here, you have 8 choices, right? It just can't be the same as either of these two. Remember, this one is a 0. All right, so I'm not worried about putting a 0 here because we're not going to put it anyway because we already have it here. We're trying to keep everybody different. So you have 8 choices for what to put here. So this one is, okay, this one is a 0. This one is not the same as the 1s. And this one is not the same as 1s or 10s. Okay. So the total number of 3-digit numbers that end in a 0 and have all different digits is 8 times 9 times 1, which is 72. Okay. Good? Okay. So then I'll let you inside my thought process, which I can kind of follow on this paper that I scribbled on. The next thing I started thinking about was, okay, the ones that don't end in a 0. So put your pencil down and just, because I'm going to show you what I was thinking and what made me realize that what I originally tried wasn't going to work. I'm going to turn this off. Okay, so when I started thinking about don't end in 0, I said, okay, it started out all right. I thought, all right, I have 4 choices for what to put over here because it has to be even, right? And then I started thinking about what to put here, and I thought, okay, well, it just can't be the same as what's there. So I think I have 9 choices for what to put here. And then when I started thinking about the hundreds place, that's when I realized I had a problem. Can you kind of sort of see the problem? I don't know how to count this now because here's the problem. It can't be the same as what's here. Okay, that's no problem. It can't be the same as what's here. That's no problem. But it also can't be 0. You cannot have 0 as a leading digit. And I don't know whether or not I used a 0 right here. That's the problem. And if I don't know whether I used it here, then I don't know if it's something I have to worry about here. All right? And so what do you think I realized I had to do? I had to take this case, 3-digit numbers that don't end in 0, and do what?
0 in the middle case?
That's right. I had to use 2 little subcases. All right. And that ended up working. All right. So let's make case B don't end in 0 but have 0 in the middle. Okay. So that'll work out fine. We have 4 choices for what to put here. We have 1 choice for what to put here. So this can be 2, 4, 6, or 8. This has to be 0. And then how many choices do I have for what to put over here? I have 8, right? I can't use 0 because it's already been used, and also because it can't be the first digit. And I can't use whatever I used here. So you have 8 choices for what to put here. Okay, so again, your 8 choices are just anything except what you already used. So in this little subcase, there are 32 choices. Okay. And the last little subcase is, what about the ones that don't end in a 0, or let's just say don't have 0 in last 2 digits? Okay. You have, I think I can just barely squeeze this in, you have 4 choices for what to put here. Remember, all these things have to be even. You have how many choices for what to put in the middle? Anything except what you already used here, but also not 0, right? So you have 8 choices for what to put here. Okay, and then how many choices do you have for what to put here? You have 7, right? You cannot use whatever you used here and here, and you can also not use 0 because 0 can't be a leading digit, and that's the only reason. You have 7 choices. So I'm kind of leaving it up to you. I ran out of room there. I'm leaving it up to you to scribble in an explanation to yourself of, why were there 7 choices. Not the same as this, not the same as this, and also not 0. And 7 times 8 times 4 comes out to, I wrote it down, 224. 72 plus 32 plus 224 comes out to 328. And lo and behold, 4 plus 41 plus 328 comes out to be exactly the same thing that your classmate got when he did a computer simulation 373. So somehow, and it would be kind of interesting to look and see how this happened. The answer we got in class the other day was 405. So somehow I picked up an extra 32 that I shouldn't have had. I don't know exactly how that happened, but anyway, I am completely 100% convinced that 373 is the right answer. All right? All right. You want to see the even easier way to do it? See, what's a pain in the neck about counting the even numbers is all this worrying you have to do about 0. So what's easier, I was going to say even easier, but that would suggest that this was easy. What's easier is count indirectly. Count, yeah, right. Indirectly. Instead of directly counting the number of numbers that have distinct digits and are even, is count the total number that have distinct digits, which we already did, and which I'm going to ask you to remind me what that came out to. And subtract the number that have distinct digits and are odd. And that turns out to be a lot easier to count. Okay. Can somebody look at your notes from last Tuesday? How many, what was the answer to letter E? I want to say it was 700 something. 738? Okay. So, right? So now let's count the ones that have distinct digits and are odd. That's easier. So you still have to do, I think you still have to do the 3 cases. 1-digit numbers, there are 5 of them, right? 1, 3, 5, 7, 9. 2-digit numbers, look how much easier this comes out when you don't have to worry about 0. If we want these things to be odd, we have 5 choices for what to put here. And then you have 8 choices for what to put here. Just don't use what you used here, and don't use 0. 8 times 5 is 40. And then the 3-digit numbers, 5 choices for what to put at the end. 1, 3, 5, 7, 9. Let me think about this for a second. Oh, this one we might have to break into. This one I think we have to break into subcases. Okay. Because we run into the same problem. If we try to count all of these at once, remember the first digit can't be a 0. And so I'm going to have to worry a little bit about whether or not this was a 0. So we'll do 2 subcases, 0 in the middle. It's not as many cases. 0 not in middle. Okay. So if you have 0 in the middle, that's 1 choice. And then 8 choices for what to put over here, right? Don't use 0 and don't use this again. So that comes out to 40. 0 not in the middle. You still have 5 choices for what to put here, and now you have 8 choices for what to put here. Don't use the same number you used here, and don't use 0. And then you have 7 choices for what to put here, right? Don't use the 1's digit again, don't use the middle digit again, and don't use 0. I'm just trying to think if there was an easier way I could have done that. I feel like when I did this last week, it wasn't quite this much work. Okay, anyway, that comes out to 320. So now you do 320 plus 40 plus 5, which is 365. And look what happens when you subtract 365 from 738. Dun, 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 dun. Same answer. And that's kind of interesting because I remember somebody guessing, and I believed you, because it sounded completely reasonable, that the number of even numbers and the number of odd numbers should have been the same. All right. Well, now I can kind of see why they're not the same. Well, can I? Okay. I wouldn't have been surprised if they came out the same, but actually they're 8 apart. Right? There are 8 more even numbers than there are odd numbers. So that's kind of interesting. All right. So hopefully that makes things a little clearer. I know, again, I made a mess of this last Tuesday when we did it, and every time I do this example, enough time passes where I forget how complicated it is, and so yeah. All right. All right. Questions? Any questions on 6.1? I just realized that, and then we, okay, I already did that example. Okay. All right, so this is something that I sometimes do and sometimes not. You'll notice at the end of the PowerPoint for 6.1 is your homework assignment. And I'm pretty sure that by this point last year, I had gotten the message that up until that point I had been assigning too much homework. All right, so I cut it down. If it feels like a lot now, it was even more last year because I didn't think about the repetitive, letters A through M. Right? And so now whenever I see that a problem has more than 4 parts, I have you do like every other part. There haven't been as many like that, though, lately. What I might do, if I think of this tomorrow, because you're not going to have to turn in this homework until exam 2, and I'm not really thinking yet about when that's going to be. The soonest it'll be is not the week we come back from break, maybe Thursday of the week after that, maybe. All right? I don't think it'll be any sooner than that. When I think of it, maybe I'll try to do it tomorrow. I will look over this assignment and see. I think there might be some counting problems in here that have like letters A through something. And so I'll look at that, and if something looks really repetitive, I'll pare it down a little bit. All right? So, yeah, so that's where we are. All right. Any questions? While you're deciding whether you have questions, I am going to post so that you have them. The notes for 6.2. Sorry I didn't do that before now. Like I said, I've been kind of flying by the seat of my pants. My whole Sunday was dedicated to you guys, working on the exam. And that was totally my fault because I had let it go for a little bit too long. Okay. Oh, rats. I know what I wanted to do before I came to class. The proofs page, that last page, that was a little eh. It was, some of them were actually pretty good. Not too many people, so there were 18 points available on that page. Not a lot of people got 18, but a pretty decent handful of people got 15 out of 18. And for proofs, I'd say that's pretty good. Some people didn't get very many points on that page at all. Just did not get the, really anything about the proofs. So that was a little disappointing. Like I said to you, I know they're hard. They take lots of practice. That's why, for example, I put 4 of them down and I said pick 3. All right. But anyway, at some point, I am going to show you. Oh, you know what I might be able to do? They probably have a scanner downstairs, don't they?
I think they copy it.
Yeah. Maybe I'll see if I can send a scan of it to myself, and then I'll project it up here onto the board. Okay, so stay tuned. I am pulling up notes for 6.2. So you might need to refresh your Blackboard page. Okay. Right about now. Okay. All right, and then I'm going to open this. Okay, so after you refresh the page, you should see that 6.2 notes are there. Oh, the pigeonhole principle. That's so much fun. I love the pigeonhole principle. It's something that sounds really, really simple. The first time you hear this, you're going to say, duh. But what's so ingenious and beautiful about the pigeonhole principle is how it's applied. All right? People have thought of so many crazy creative applications of the pigeonhole principle. Okay. All right. Suppose there are 30 students in our class. I think that's pretty close. Explain to me why you know for a fact, even if you've never met them before, let's say they're all total strangers, you don't know anybody's name, you can at least guarantee that at least 2 people in your class have first names that begin with the same letter. Why is that? There's only 26 letters. So even if the first 26 people in your class have first names that begin with the letters A through Z, person number 27 is going to have to duplicate one of those. All right? That's exactly the reason. It's basically because 30 is bigger than 26. Okay? All right, well, that's an example of the pigeonhole principle. So the pigeonhole principle says that if k is a positive integer and k plus 1 or more objects are placed into k boxes. So think of the letters of the alphabet as being the boxes, and think of the students as being the objects. So I put each student in the box that corresponds with the first letter of their name. All right, if the number of objects is more than the number of boxes, well then guess what? You're going to have at least one box that contains at least 2 of the objects. Right? For example, at least 2 students whose names begin with the same letter. That's called the pigeonhole principle. Okay? All right. So now we generalize it a little bit. Suppose there are 30 students in your class. Explain why at least 5 of them must have been born on the same day of the week. I can't tell you what day of the week. I can just tell you that if we separated people into groups based on what day of the week they were born, we would have at least one of those groups with at least 5 people in it. Why is that? How many days of the week are there? 7. When you divide 30 by 7, there are 4 with a couple left over, right? So let's say we took 7 times 4, which is 28. Worst case scenario is that of the first 28 people, 4 were born on Sunday, 4 were born on Monday, 4 were born on Tuesday, etc., etc., etc. But as soon as you get to person number 29, that's going to be number 5 in somebody's group. Okay? So that's an example of what's called the generalized pigeonhole principle. So we generally use this whenever the number of objects is like much bigger than the number of boxes. All right, so let me explain this a little bit. I know we've talked about floor. I don't know if we've talked about ceiling. I was just talking to my Calc 2 class yesterday about the floor function. We needed it for something. So in my example, big N is 30 and little k is 7. We're putting 30 students into 7 boxes that correspond to the day of the week they were born. So if you do 30 divided by 7, that comes out to 4 point something something something. What this is saying to do is to round that up. Maybe in honor of Rounded Up Pi Day, which was last Monday. Oh, speaking of which, I got, I have to sort through these, but I wanted to let you know that I have Student Math League results, and I have Integration Bee results. So again, I just have to go through them and figure out how much extra credit everybody gets. Okay, so when you do 30 divided by 7, you get 4 point something something, and what this notation means is round that up, and that rounds up to 5. You want to hear something great about Student Math League? So didn't I say to you guys that, when I was describing to you how it worked and how we have first prize, second prize, third prize for the total score for the year, didn't I tell you that it has happened where first place, second place, or third place goes to somebody who only does one round of the test? You remember me saying that? Well, we had an extreme example of that this year. 2 out of the top 3 only did one round. One person did only fall. One person did only spring. But they did so well that they ended up in the top 3. All right. So I thought that was kind of interesting. All right. So I don't know at what point we tell them that they were first place, second place, third place. So I'm not going to say anything because I don't want to spoil anything. All right. It's been a while since I've looked at this. So a toy box contains 10 red blocks and 10 blue blocks. That's right. This was before I figured out animation. A child selects blocks at random without looking at them. How many blocks must she select to be sure of having at least 3 blocks of the same color? To be sure of having at least 3 blocks of the same color. That wouldn't be a bad Student Math League question, actually. It's not that hard. You just have to think about it the right way. How many? So kid closes her eyes and starts picking blocks. She has to pick 5, right? Okay. As long as we don't care what color, then 5 is enough. Okay. Worst case scenario, think about worst case scenario. She picks 4. She could pick 2 that are red and 2 that are blue. But as soon as she picks a 5th one, it's either going to be red or blue, right? Does that make sense? So it's one of those problems where, there's really, you don't need a formula, you don't need any kind of fancy mathematical thing, you just have to think about it. Okay. Does it make a whole lot of difference to reword it to say how many blocks does she have to select to be sure of having at least 3 that are blue? How many? 13! She has to pick 13 if she wants to guarantee having 3 blue. Because, again, worst case scenario, first 10 are all red. And then she has to pick 3 more in order to get 3 that are blue. Okay. So, if you're trying to make these answers a little more mathematical, you could think of this as 2 times 2. All right? 2 of the same color, and there are 2 different colors, and then add 1 more block and you're guaranteed to have 3 that are the same color. Here I think we just need to say 10 plus 3. Make sense? Okay, what else we got? Just trying to think. We're coming right around. You know what? This would be a good think about it during the break problem. I would like you to... All right. So, show that if 6 integers are selected from the first 10 positive integers, there must be a pair of those integers with a sum equal to 11. This is where we get into really ingenious examples of how to use the pigeonhole principle. Okay. All right. So, I don't know how you approach something like this if you're just thinking about it for the first time. You start thinking about the numbers in the problem. So the first 10 positive integers, I know what that means. Which is the pen I don't like? It's not this one. We know what the first 10 positive integers are. Okay. So, well, you could start by just trying it, right? See if you can get around doing that. So let's just pick some numbers. So pick your favorite number between 1 and 10. 3. Okay. So let's say the first number I pick is 3. Well, I'm trying to avoid picking any pair with a sum equal to 11, so let's not pick 8. Okay. All right, but we can pick anything else, right? Like, for example, 6. Okay. I think I heard 6 a split second before I heard 5. Unfortunately, if we pick 6, we cannot pick 5. Because those are going to add up to 11, right? Okay, now notice that in this particular case, oh no, we're just trying to avoid pairs of numbers that add up to 11. Can you kind of see where this is going? We have to pick a total of 6. All right, so what would you like to pick next? 9. We can pick 9, but that means we can't pick 2. 1. If we pick 1, that means we can't pick 10. So how many do we have left? We can pick 4 or 7. Pick 4. And now you can't pick 7, and now I think we've run out of things to pick. If we pick anything else, we're going to have 2 that add up to 11. So you see where the 6 comes from? Why it's guaranteed you'll end up with a pair that add up to 11 if you pick 6, right? Because I started by picking 5, and each time I picked one, I crossed out the one that would make it add up to 11. So if you pick a 6th one, you're going to have to pick one of the ones that I said you couldn't pick, all right? So I think the nicest way to present this is just pair the numbers together in pairs that add up to 11. So 1 and 10, 2 and 9, 3 and 8, 4 and 7, 5 and 6. Okay. And the way that you really work the pigeonhole principle into it is to say we're picking 6 integers from 5 pairs. Okay, so the integers are like my objects, and the pairs are like my boxes. And so by the pigeonhole principle, at least 2 of these integers come from the same pair, don't they? And I would consider that a proof. All right? The only other way I know to prove this is you're familiar with the idea of brute force, I think, as computer science people, right? Brute force is where you just try every possible combination, right? Brute force hacking, all right? That's something you could do with a simulation. All right, you could set up a little computer program that would actually pick every single possible group of 6 integers out of the 10 and use your computer program to show that there's a pair inside that set that adds up to 11. All right, that would be a very clunky way to do it. All right, this is a lot shorter. Okay. So does that happen if you only pick 5? Will you get a pair that adds up to 11? No, I think we showed that before, right? Even if you do what I call worst case scenario, well, look at the ones we picked. I don't think any of those add up to 11. 1, 3, 4, 6, and 9. There's no pair of those that adds up to 11 because we only picked 1 out of each pair, right? We picked exactly 1 out of each pair. That's one of many examples. All right. There's a whole bunch of different examples like that. But no, there has to be at least 6 integers if you want to guarantee there's a pair that adds up to 11. Okie dokie? All right. So, let me see. Blackboard for when I figure out what the official homework assignment is for 6-1, I'll put it in the usual spot under homework on Blackboard. Okay?
Cool.
Thank you.
All right, so we're going to do Maple today, but you are not going to do Maple on your computers. Nope, don't even start Maple on the computer. But we are going to do Maple today, and yes, that makes sense. So what we're going to do is we're going to look at recursion. We're going to look at some recursion algorithms in code, and we're going to figure it out with pen and paper what the answers are. And I'm going to do a couple of examples, and then I'm going to throw some up here, and then we'll make a game out of it. Who can figure out what the answer is? Yeah, as long as it's not Maple. You're not actually programming if you're just writing. It's fine. All right? So, like, there's different techniques you can do to figure out something like this without actually programming it and hitting the run button and having it run and give you the answer. Okay? But I'm going to show you how, one way that you could do it by hand. So, like, let's say we have this recursive procedure. And we call the recursive procedure and we give it the input of 7 for n. So n equals 7. So we're going to call example 1 with n equals 7. And I actually write it like this. So example 1 with 7 as our input. What's going to happen? 7 doesn't equal 1, of course. So we go down to our else statement and when we return, and here's our recursive call, we're going to return example what? Example 1 with the input of 5, 7 minus 2, which is 5. So you can just write the 5 if you want, or you can put 7 minus 2, plus 7. Okay? So that's what, when you call example 1, that's what it's going to give us. Now I'm going to call example 1 with 5 as the input. 5 doesn't equal 1, so he goes to the else part. He's going to call himself again with the input of 3 plus that 5. Okay, you can start to see a pattern here. He doesn't equal 1, so he's going to call himself again with the input of 1 plus the 3. He's going to come down and he's calling example with 1 now, but if n equals 1, we return 2. So you can start moving back up. So this is going to be replaced by 2. 2 plus 3 is 5. 5 plus 5 is 10. 10 plus 7 is 17, and it's going to give you an output of 17. Okay, so you move down in your recursion, you move back up. Let's do one more example. I prepared 2 examples today. Okay, this one has 3 branches in it. All right, so these 3 branches, okay, well, we're going to call it again with the input of 7. Okay. So when we first call this thing, we're going to give it the 7. So So you throw 7 in there. 7's not equal to 0. Remember what your mod does? It gives the modulus operator. So 7 divided by 3, well, 7 mod 3, is it equal to 0? Meaning, is it divisible by 3? No. It gives you a remainder of 1, so that's false. So it'll go down to the else part. And when it goes down to the else part, it's going to call itself again. And this time it's going to give itself what? 6, right? Because 7 minus 1 is 6. This guy's going to call the function, or it's going to give the input, or g equals 6. G doesn't equal 0, but is 6 mod 3 equal to 0? Yes. So he's going to go into the else if part, and he's going to return 3 times himself called again with what as the input? 5. Okay, so now we return again. We're calling ourselves again. G equals 5. 5 doesn't equal 0. 5 mod 3 does not equal 0. Comes down to the else part. And it gives itself 4. Okay, again, you can plug 4 in there. False, false, goes to the else part. Okay, calls itself with 3. The if is still false, but now is the else if true? Yes, because 3 mod 3 does equal 0. So when he calls it with the number 3, we're going to give it 3 times, calling itself again with 2 as the input. Okay. This guy goes into the function. The if part is false. The else if part is false. So it goes to the else part. And it calls itself with the number 1. Now we've reached our base, wait, not yet, actually. Because my base case is g equals 0. Okay. So we're calling it with number 1, so it's false. Is 1 mod 3 equal to 0? What's 1 divided by 3? 0. Remainder. What's the remainder? It's 0, remainder 3. Okay. Okay. So then it goes down to the else part. It calls itself again with 0. And now we've reached our base case. And what do we return when we reach our base case? 2. So he gets replaced with 2. He gets replaced with 2. 2 times 3 is 6. 6. 6. 6 times 3 is 18. And that's your answer, is 18. That's what it'll spit out at you. All right. This is one way that you can kind of write it out. Okay. All right, you guys ready to play? So I have some mystery ones that I made. I hid them in here, so you can't see them right yet. So I'm going to make them available. So if you want it, well, I should just show them up here. We'll just show them up here. Dun, dun, dun. So what I was going to do is the first person to get the answer gets to pick any of the fabulous prizes. Or any of the books over there, too. You can have a book if you want. Okay? So you have to tell me what the output would be when we call it with giving it the input of 5. Yeah. And once you get it, raise your hand real high so then I know you got it. Then I'll ask to see your answer. What do you get? You have to tell me what its output is.
Oh, it's not.
No.
Oh, wait.
No. What do you think, Victor? Yes. Good. Good. It is, what was it, Victor? It was 15. And just for practice, I told myself I would do these with you. So if we called it with 5, the if statement's false, it goes to the else part. And you can, well, I guess you can pick a prize at the end if you want. Wait till. But it will return 5 plus calling itself again with 4. This guy is going to be 4 plus calling itself again with 3, right? Because we can kind of see a pattern here. These always make patterns. Okay. This guy calls itself 3 plus calling itself again with 2. 2 plus calling itself again with 1. This guy would be 1 plus calling itself again with 0. And then that's our base case. So he returns 0 plus 1, so he returns a 1. Yeah, put the 1 right here. 1 plus 2 is 3, so he returns a 3. 3 plus 3 is 6, so he returns a 6. 6 plus 4 is 10, so he returns a 10. And 10 plus 5 is 15. So he returns a 15. Okay? And that's what it's doing in your computer. Every time that it's calling this thing, this one's just put on hold, it calls the next guy. This guy's put on hold till this one's finished. This one's put on hold till this one's finished. This one's put on hold, this one's finished, this one's put on hold, this one's finished. And when they're put on hold, it's called putting it on the stack. And when you write really bad recursion and it never ends, it'll say stack overflow. So if you ever get that error, stack overflow. It means the base case was never reached and you overloaded the stack. Okay? All right, let's try the next one. I got 3 of these. They get harder. This one's a little bit harder. All right. See if you can get this guy. And trust me, you do have to kind of write these down. Even I have to write them down. And the videos could be like the whole time. I'll have to fast forward this part. Do you think you got it? Hold on. You have to show me. You can't call out. Yes, actually. Yeah, you're pretty good at this. Actually, people usually find this difficult, so it's very good that, you know, it's pretty good that you can, like, actually do this. No. Victor got it. That's good. We'll give second place for this one. Yes, good. Yes.
I remember we did this.
Yeah, in 39 I do this too. I decided to do it this year in Maple also. Maybe we'll do top 3. You get it, do you think? No. No. Yes. Good. You didn't look over here, did you? Just kidding. Just joking. That's good. All right. And the more you do these, the better you get at them and the easier they are. They get really, you know, cinchy after a while. And this is good practice for recursion. You could look up recursive, you know, algorithms online, try to do them by hand, and then run them and see if you can get them. It helps you think recursively. Let's figure it out. Let's figure it out. Okay, so I'm just calling it with 3. Okay, so obviously we don't go in the if part, we're going to go to the else part until we get less than 0. Okay, so this guy is going to return 3 plus calling itself again with 2 plus calling itself again with 2. Okay, what is this guy going to return? 2 plus calling itself again with 1 plus calling itself again with 1. What's this guy going to return? 1 plus calling itself again with 0 plus calling itself again with 0. And what's this guy going to return? And I haven't even started on these guys. And then this guy is going to be 0 plus calling itself again with -1 plus calling itself again with -1. Okay, because 0 minus 1 is -1. We've actually reached a bottom point here. We can expand the rest too, but this is how it's running your computer. When it calls this guy, it doesn't look at this guy yet. And it calls this guy, it calls this guy, it calls this guy. Okay. Now, what is he going to return when he calls itself? Yeah, we've finally reached the base case. So it's going to give us back 2 here. It's going to give us back 2 here. So what's going to return here? 4. Now, this is doing the same thing. So we could write it out. You could write him out. He's going to give you 0 plus m -1. And I'm writing sideways here. But what's he going to give back? 2, 2. He's going to give back 4, 2. So you can kind of assume when they have the same value in there, we know it's going to happen. But notice that it does break it down like this. It does do all of this recursion in your computer. This is why recursion is inefficient. Okay, it really is always more inefficient to do things this way. Okay. So this will be 4 plus 4 plus 1 is 9. So you know M1 is 9. 9 plus 9, 18 plus 2, 20. This guy will be 20. 20 plus 20 plus 3. And that is the answer. If you ran this thing, that will be your answer. And I didn't even write down all of the branches because these two were the same. But note that all these branches would come out and be executed by your computer. He doesn't realize that these are the same, like we do. All right. Okay, so this is our most challenging one, this last one. Mystery 3. Okay, you guys ready? On your marks, get set, go. So here's our mystery 3. You guys remember what floor does? Floor takes you to the floor. It rounds down, always rounds down. This one you definitely have to write out. Okay. This is good practice. If you can think recursively, then these recursive algorithms will be much easier to understand. Okay? And the answer is... No, it's
Right.
actually much bigger than that. Remember to kind of write it out. It's really hard if you don't. So. You got it?
I'm not sure if I did this right. When it recalls it, and then it's kind of views, right? Not the,
And this is your answer?
yeah, I haven't added that yet.
And add it up, and then I think it is their answer. Yeah. It'll give one answer. Yes, that is the right answer. Good. I've noticed that, actually, because I've been teaching recursion for a while, that some people get recursion really easy, and some people, it's a little bit more work for them. And that's okay if it's more work. And I've noticed, too, that if you do practice, you do get better at it. It is something you can practice and get better at. Okay?
I got it wrong.
Oh. I had this one student, Igor, and he would just get cursive problems like... He was pretty amazing.
Start with this. And then
Close, but a little bit off. Think you got it? Wait, what's your answer? That's what Todd got, but that is not the right answer. But it is what somebody else got. Let's see if a couple more people get it. Remember, you do have to kind of write it down. You just write down all of your steps. Got it. Close, but no, that's what Yesenia got actually. It's funny, or maybe that's what Michael got. It's some people we'll get kind of similar answers, but then you missed something. And you can run these, and you can trace these variables. So I'll make them visible at the end here, and then you can run them and trace the variables if you want. In fact, I'll even post the MW file. Because when you trace the variables, it'll help too. Huh?
this one.
No, it's a little bit bigger. Does anyone else want to try their answer? We'll give like one more minute. One more minute. I wish that was the answer right now. It's bigger than that, yes.
Yeah, then you're right. So that'd be...
Because remember that every recursive call has to complete itself. Wait, do you think you got it? Yes. Good. Yay. Okay, good. Nope.
Oh.
Good. All right, so let's do this one actually. And you can continue to work on yours if you are almost there. But okay, so when we call this thing, I gave it the input of 3 and 35. Okay, so that's my A and B. Our stopping case, our base case, is when the second argument is 0. So we know the second argument is going to get smaller, which it does. Okay. So obviously we're not going to get to that base case until it's 0. So we can just kind of think, okay, till the second argument 0, we're not going to return any return 0. So then we say, okay, what is the second statement saying? If b mod 2 equals 0, what's that mean? If this is even, we'll go into the else if part. Okay, so you can kind of think of it that way. If this is even, we go into the else if part. And then if this b is odd, we go to the else part. The else part is calling mystery 3 again, so we're going to go to the else part. And it gives to us a plus a, which is 6. Floor 35 divided by 2. What's floor 35 divided by 2? You guys tell me. Yeah, 17. Plus what? Plus a, and a is 3. Is this going to go into the else part? Or I mean the else if part? No, because he's odd. So we know that it's going to go to the else part. He's going to call himself again with 6 plus 6, which is 12. And floor b divided by 2. What's 17 divided by 2? Floored? 8. Plus a, which happens to be 6. Okay, now he's even. Now we're going to go to the else if part. The else if part says return this function. Call again with a plus a. So 12 plus 12 is 24. And floor b divided by 2. So 8 divided by 2 is 4. Yep, so it would be 4. And there's no plus a here. He calls himself again. He's even. So we know we're going to go to the else if part with 24 plus 24, which is 48. And this divided by 2 floored, which would be 2. Yeah, when the b is an even, then we know we go to the else if. Okay. So M3, so it's even again. So we're going to say a plus a, which is 196, right? 96. 48 plus 48. Plus floor of b divided by 2. What's 2 divided by 2? 1, and it's floored. It will be 1. Have we reached the base case yet? No, this isn't 0 yet. Okay. Now he's odd, so we're going to go to the else part. The else part says call yourself again with 96 plus 96. Actually, it doesn't really matter all that much. He's something, right? And the reason that he doesn't matter is, well, we'll just say he matters. Okay, it'll be, let's see here, 18 plus 192. Okay. And then we're in the else part. So it'd be floor b divided by 2. What's 1 divided by 2 floored? 0. And then we have to add the a. He's odd now. Or actually, he's our base case. So what's our base case return? 0. We replace this with 0. 0 plus 96 returns 96. This guy returns then 96. This guy returns 96. This guy returns 96 plus 6. What's 96 plus 6? 102. 102 plus 1 plus 3. It would return 105. And that is your answer. So, it's okay if you found this hard. Actually, that's good. It means you just need to go home and practice. I'll put a couple of links to some sites where they have problems like this. Try to do them by hand at first. And then try to write them out, in programming code and even trace the variables. And that will make you better at recursion. You will get better at it. Because recursion, yes, is always more inefficient, but it has a lot of really neat applications. Okay? Like really high-level kind of sorting applications, which are in your book. In fact, on Thursday, we're going to talk about the linear and binary search with recursion. And then we're going to look at merge sort and quick sort and test merge sort and quick sort, the way that we tested the other sorts, counting the comparisons and counting the swaps. Exactly. We always find that fun. All right? So make sure you read that section in your book. I think it's the algorithm part of chapter 5. We're going to do that on Thursday. Okay, they go over those algorithms. And I'll post these. I'll make them visible and post the code. Okay, so you can run them. Oh, and people who want